was a pretty good description of Dutch people, I think. But don't worry, I won't say anything impolite. Let's see. Wait, not that one yet. This one. Does anyone have an idea what's pictured on this screen, on the photo? RAM, I hear. ROM, SSD, I hear something. Processor. It's basically all kinds of chips, right? So who here doesn't have a laptop or a smartphone? That's a trick question, of course, right? Everyone has one. Chips are in these devices, but also in a lot of other devices. We saw the presentation from Electrolux. Nowadays, you have chips even in your microwave to make it heat up before you arrive home and things like that. Chips are everywhere, basically. And I'm here because I work for ASML, and we provide the machines that big corporations like Intel and Samsung and TSMC, who makes the chips for Apple, and all the other chip manufacturers, they use our machines. So the chance that one of your chips or a lot of your chips were created on one of our machines is pretty big. On the newest generation, for the most advanced chips, we basically don't have any competition. But don't worry, it's not a marketing pitch. I won't try to sell you one of these machines, because one machine costs 300 million euros, which, if I did the calculations correct, is about 6,000 million leis. So I don't have that in my bank account, and I guess you guys also don't have it. But I joined this company a couple of years ago, and then I realized that I've been using computers for so long without actually knowing how the chips were created inside those computers or inside any device, basically. And I learned quite a bit about that, and I thought, like, why not share that with other people as well? So now today I will try to learn you a bit on how these chips are physically created. There is a bit of Java in it as well, but if you don't have any Java experience, don't worry. It's relatively high over, and I mostly focus on the creation of the chips. Oh, that was one too fast. Yeah. Anyone, any Java developers here? I see a few. What's on this one? It's the Duke, I hear it. It's the Java logo. And what's underneath the Duke? A silicon wafer, indeed. So this is basically the basis on which chips are created. And on this wafer, I printed 564 Dukes. That's also more or less the amount of chips that you can have on one single wafer, depending on what type of chip. If it's, for example, a sensor, they are smaller, so you can print more on one wafer. If it's a processor, they are a bit bigger, so you have a bit less on them. But that's an indication on how many of these chips are created per wafer. And actually, when I created this, I was still learning about it. Later, I learned that normally the chips are printed even on the edges. So part of the chips basically don't function because it goes over the edge, and we will see that later as well. With these kinds of chips, the basis is often the transistor. Maybe you have heard of it. In the past, you could easily photograph them like this. It was still fairly big. And basically, the race is to create as small transistors as possible. And a transistor is basically like a water tap. Water flows in, you control it, and then some water comes out. And a transistor does the same, but then with electricity. The number of transistors is often defined by Moore's law. There are a lot of explanations for the law, but the simplest one is basically that the number of transistors doubles every 2 years on the same surface. And that's already going on since the 70s, which is really weird, right? Which other profession or thing do we know where stuff doubles every 2 years? I mean, cars don't go twice as fast every 2 years. Buildings aren't built twice as tall every 2 years, but somehow with transistors, we managed to do that already for 50 years. So anyone an idea how small transistors are nowadays? So I put some numbers in, and keep in mind 1 million nanometer is 1 millimeter. It's, for me, still difficult to comprehend the smallness, but any idea how big a transistor is now? $400? Yeah, around 4 to 10, 2 to 10, that area. It depends a bit on which marketing stories and things around it. There are some debates sometimes, but it's in the really small categories here. So if you compare it to, for example, the growth of human hair, that's more or less the size of the transistors that we create. It's really small. And I already showed you that wafer, and to give you a bit more context about it, in one machine we can process about 330 wafers per hour, depending on the machine, and that means we create one layer on it. A chip can contain up to 200 layers, depending on the type of chip, so it will need to go through those machines 200 times. And yeah, there are some more numbers. The one I find really impressive is the 140 million transistors nowadays per square millimeter. Yeah, that's, for me, it's insane that we managed to create something that small and do it continuously. It's not a one-off. These machines, they run 24/7 the entire year. So how does it work? It's a bit like a 3D printer. Maybe you had a 3D printer yourself. The 3D printer prints lines of molten plastic basically on top of each other. With chips, we sort of do the same. We also print layers on top of each other. But we do that with a bit more accuracy than your home 3D printer. Our accuracy, if we compare it to a real life thing, is, let's say you drive on this line for 300 kilometers, then you turn around, drive back the same 300 kilometers without deviating more than 2 millimeters in the entire road. That's the efficiency with which we print lines on top of each other. And it all starts with a wafer. And that wafer, it gets a chemical coating. We call that resist or photoresist. And that's basically the first step. And what's maybe also interesting to mention is that in this whole process, there are several companies involved. So we produce some of the machines, but there are also other companies that produce machines. Like this applying resist is not one of our machines, but later steps will be done by our machines. So it's like a chain of machines from different vendors that create these chips for you. Next step, it goes in one of these. So this is a machine from us. Nowadays, these machines are so big that you need 3 fully loaded Boeing 747s to transport one machine. Some say it's the most advanced machine produced by mankind. Yeah, I'll leave that up to you to decide. I'm not really objective in that. And then in that machine, that wafer is put on a magnetically levitating wafer table. And why do it so difficult? Why not clamp it or something? Yeah, if we clamp it, it would already bend a little bit. So the chance of having chips that don't work perfectly well is bigger. So we do everything to prevent issues from occurring to those chips. That's why basically the wafer is floating on top of that wafer table. And now I will show you in the next video how that looks and what happens. So basically on that resist, we will do something, and that's shown now. So this looks a bit like science fiction, so I'll try to explain a little bit what happens. Basically, we have a laser amplifier. So when you saw the huge machine, the laser amplifier is in the basement. It's not even part of the machine. It's also really big. It amplifies a laser pulse to 40 kilowatts, and then that laser beam travels for 30 meters. And at the same time, we have molten tin droplets being ejected at a speed of 70 meters per second. Then that laser beam hits one droplet of tin. It flattens the droplet of tin a little bit in a pancake shape. And then a second laser beam hits that droplet of tin again. That results in plasma being emitted, which results in EUV light. And that EUV light we need in the end to shine on the photoresist on the wafer. This process, so that shooting twice on that droplet of tin and emitting EUV light, happens 50,000 times per second. When I first saw it, I was impressed that it even works once, but this happens 24/7 at this rate. So without splattering all the tin around in the machine, because that would also cause all kinds of issues. And the plasma that's being emitted is basically the same temperature as the surface of the sun. So we also need special gases to then cool off the machine again between each time that we shoot. So there is a lot more going on than was shown in this video even. And then basically the EUV light that's being emitted, it needs to be transported through the machine. And for that we need really smooth mirrors. Because the problem with EUV light is that it quickly disappears. So we need to do everything we can to make sure we keep as much of the EUV light as possible. So these mirrors, if you would extract them to the size of the world, the biggest bump would be less than the thickness of a human hair. These are special mirrors with 100 layers of special coating and chemicals to be as smooth as possible. So, and what I also really find interesting in this business is that while we try to print smaller and smaller details, the machines actually get bigger and bigger with each generation. In the old generation of machines, one mirror would weigh 123 kilograms. Our latest generation of machines, one mirror weighs more than 1,000 kilograms. So yeah, the machines basically become really huge. And then basically this happens. So what you see at the bottom right is the laser or the EUV light coming through, shining through some mirrors. And then at the top you see what we call a reticle. And then it goes through to the wafer. And that reticle, it basically contains the pattern which we want to print. It's a bit like the template or stencil. Maybe you had one of these when you were younger. There are parts where you can draw in, and some parts they are covered up, basically. It's the same for a reticle. The reticle contains the pattern which we want to print for that layer, so the transistors or the connecting layers that we want to print are in that reticle. And that reticle then makes sure that pattern is printed on the wafer. And then you think it's fairly simple, right? If we have a 3D printer, we print a pattern, the 3D stuff is just stationary, it doesn't move, and then layers are printed on top of each other. We do it a little bit faster. So for us, the reticle moves nowadays even with 32 Gs, the newest generation of machines, and the wafer table moves with also a lot of Gs in the opposite direction. So they move like this while printing the pattern. So they somehow manage to make sure it's printed on the correct position on the wafer. And that's the only way that we can print so many chips in a short amount of time. It looks like this. So here you see that light shining through with the patterns being printed. This is the reticle you see at the top of the machine. And this is then the entire machine. So at the top you see reticles being changed and being used. At the bottom you see the wafer tables and basically making sure that those are being moved. You see two wafer tables. The reason that we have two is on the first one we calibrate it. So we make sure the wafer is correctly positioned before we go and shine the EUV light on top of it. That way we can parallelize some of the work. But even while the EUV light is shining on the wafer table on the right, we still adjust that wafer thousands of times per second to make sure it's perfectly aligned. And if you look at it like in a diagram instead of in some cooler pictures, it looks like this. So we started with that wafer. We put some photoresist, some chemicals on top of that wafer. Then we have that reticle, EUV light shining through. Some of the EUV light touches the photoresist and some doesn't. And then we can do one of two things. We can either keep the parts that are touched by the EUV light, or we can remove them. So afterwards, there will be a step where this resist is removed. And then it looks like this. So this is the circle. For each layer, you have to go through the entire circle. So if you have 200 layers on a chip, this circle is covered 200 times. So for example, we saw that photoresist coating. The exposure is basically the printing of the layers with the EUV light, and then the developing, baking, and all the other steps will happen. And then in the end, you have wafers like this with real chips. So you see here that on the edges, basically, there are also chips printed. I often get the question like, hey, why do you print them on the edges? It's a waste, you know they won't work. Or why don't you have a rectangular wafer? Then you can just print nicely all your chips on it. From what I understood is that the circle is better, and it gives a higher yield, better chips that are functioning. Probably because if you make it a square, it will bend more easy and you will have some more issues. So they did a lot of experiments. In the past, they also had smaller wafers. Nowadays, they're like 30 centimeters. They also did tests with bigger wafers, but apparently, most cases, 30 centimeters is the ideal size to get as much functioning chips as possible. So yeah, then you have all these chips being made, but you want to have as many chips and as many functioning chips as possible. That's what our customers basically want. So how to achieve that? First, we start with really, really clean rooms. If you compare it to our friends in the US, they are pretty dirty, but they probably don't need it. For us, if there is a really small dust particle on the wafer, that might already mean that the chip doesn't work. If that same dust particle is on the reticle, it means that all the chips won't work that are being created at that point in time. And if you think about a dust particle, maybe you think about the ones that you sometimes see in your home when you forgot to clean for a few days. But when I talk about dust particles, it's even particles from perfume. If you work in one of these factories, you can't wear perfume, because even that can influence the chips that are being created. So it's a really tricky environment. And us humans are the biggest contaminator. As soon as we walk in, you see all the sensors going up because they measure all the particles of loose hair or whatever that's falling off us. But even then, stuff can go wrong. Let's imagine we print a layer, we look at it from the side like this, and we print a second layer. It's a little bit off. It's not what we want, right? And this can happen in reality. So if you go too far like this, basically in the end it will break. You have a chip that doesn't really work. Or you have layers that don't connect with each other or short-circuited. In the end, we can have all kinds of issues. And as I already said, if it's on one wafer, it's annoying. But if it's something in the machine and all wafers are impacted, then it's even more annoying. Luckily, in some cases, we can do things against it. If we find out that it's a bit too far to the right, then we can try to make the next layer a little bit to the left. If all else fails, there are also some other constructions that our customers use. For example, if they try to create a 32 gigabyte memory chip and they find out that there was an issue in it, they could basically disable half of it and sell it as a 16 gigabyte chip, depending on how they design their chip. The same for CPUs. You see it sometimes that they try to create like a 4-core CPU. Something goes wrong, they sell it as a 2-core CPU. But of course, I mean, they would rather have the full chip, because then they can ask more money from their customers. So we try to prevent that. And that's where measurements and software come in. And we have two types of measurements, basically. One is things on one layer that are going wrong, and the other thing is between layers. What I showed with those lines that are falling off, basically, that's what we call overlay. So what I already told you, like we do that measurement with the wafer table, which happens 20,000 times a second with 60 picometer accuracy. So picometer is even smaller than nanometer, so yeah, it's hard to comprehend. One machine generates about 31 terabytes of data, and most of our customers have a whole load of machines. And we use all that input to basically then correct the machines. So all machines have different settings that we can use to, for example, make sure that more gas is expelled or less gas is expelled, that we try to get the temperature down, a wafer is slightly adjusted, etc. For example, this shows one, they call it a mirror, but actually it's more than 4,000 mirrors, and we can individually control their angle and things like that. So if we find out something went wrong, we can basically change stuff there. And this is just one of many things that we can change. And then you have basically the entire view of how it works. Like I told you before, it's like a chain of different machines that are being created by different companies, and you see the machines at the top basically. All those machines, they emit data. And that data can then be used to recalibrate the machines and try to improve the next run. And that's where I work on. I work on a platform which basically tries to get better results in the wafers, collect the data, process it, and do the analysis. And we do that for a reason, because in the past we had a lot of separate applications. Each department had their own applications to measure what went wrong. But that was a bit time-consuming. Data couldn't really be shared, and it was a bit of a hassle. So now we created a new platform which started a couple of years ago, where basically we make sure that all those departments can create plugins on top of our platform, and in that way share data, have the same look and feel for our support people who use the application on-premise at our customers, or even our customers themselves. And there are some challenges with it, because it's really high volume of data, but it's also completely different types of data. Some is simply text data, like, hey, this is slightly off or something. But it could also be pictures or video or AI. It can be anything, basically, that needs to go through this platform. To do that, we use Apache Spark. Basically, Spark allows you to parallelize the workload. So you have multiple physical machines, all with a Spark worker, and they process the work, and the results are sent back to the driver. It works pretty well if you have large amounts of data or heavy algorithms that run for a long time. On top of that, we have 3 types of plugins: UI plugins, processing plugins, and data plugins. So with the UI plugins, each team can customize the UI completely. If they want to have a bar plot or a wafer plot or graphs or whatever, just plain data, they can choose what they want to show in the platform. With a data plugin, they of course load the data that they want to have available. And with the processing plugin, those are triggered from the UI. They process the data that was inserted by the data plugin, and later those results are visualized in the UI. It looks a bit like this. So again, like I said, if you're not familiar with Java, we won't go into too much detail with this one. But this is like the main overview of the tools that we have, and that allow us to run this. So this doesn't run on the machine, by the way. We also have software running on the machines, but that's mostly lower level software. This runs on-premise at our customers in their data center, because there's one big challenge with these kind of things. We don't want our algorithms to be compromised, and our customers, they don't want their data to be compromised. So we can't run anything in the cloud. They are way too afraid for that. So everything runs on-premise, which has the challenge that, you cannot access it remotely and things like that. So that brings some extra challenges with it. And then in the end, we use, basically, this is the main tools and libraries which we use. But keep in mind, what I always try to give as an advice to everyone is, don't look at a stack which is shown at a conference and think, oh, this is cool, I also want to do this. This takes a lot of time to set up. We didn't start with this. We started with, for example, simple REST calls. We didn't start with Kafka. Later we added Kafka because we needed it for streaming data, for asynchronous messaging, but we didn't start with it from the beginning. And we're also still discussing if some of these solutions are still the best, or if we should replace them again with something else. So for each tool, it should fit our use case, and if not, we will replace it later or do whatever with it what we want. And I think that's also the nice thing now with all the software that's available. You can also choose. And if we find stuff that doesn't work, we also sometimes change things and contribute back even to some programming languages, because our requirements are quite high. So we sometimes encounter things, that if you Google for it, you simply get 0 hits. And the funny thing is, well, the platform, it's basically a Java platform. We basically support any language, because the teams that create the plugins, they mostly wrote software in other languages. That can be any language, like Python, C, Julia, MATLAB, whatever. And if they need to rewrite it in Java, that's quite a hassle. And sometimes those algorithms are used both on the machine and on our server. And then you definitely don't want to maintain the same stuff twice. So we have integrations with JNI and with Docker to make sure that they can easily migrate their existing stuff. So then when we have that processing plugin, the logic can still be written in, for example, Julia. And since AI nowadays is super hip, I had to include, of course, one slide about that. And I think this is actually one of the useful examples of AI. So at the top, what you see is a scan that's being made from one of our wafers. And with that scan, we can capture almost 70% of the defects. We could also slow down the scan and take 8 times as much time for it. Then we can find 100% of the defects. And then you think, it's easy, right? You slow down. But if we slow it down, we can scan less wafers. So it's either 8 wafers scanning at the same time, or if we slow it down, we can only scan 1. So it's a bit of a challenge there. And then we found out that actually with deep learning, we could improve the image at the top to the one you see at the right with the same speed, and then we can capture almost 93% of the defects. So that way, we can still scan 8 times as many wafers and possibly find issues there, while still having a high detection rate. In the end, this is what it looks like, the application. And probably when you look at it, you're like, what am I looking at? Was the same for me. I also had no clue. So we begin at the top right. Or maybe first on the left, you see the processing plugin being called. It's called test TDBB. So that was the processing plugin being run. And then the results are shown in this screen. We call this wafer plots. At the top right, you see arrows. And all the arrows point in the same direction. And above it, it says CE. That stands for correctable errors. Basically, if every point on the wafer is measured like 1 millimeter to that side, then maybe next time we should print 1 millimeter to that side, or 1 nanometer in our case. So that's stuff we can correct. On the left, you see NCE, with basically arrows pointing in all kinds of directions with all kinds of colors. The color means the bigger the change. With the algorithm that we now run, we couldn't correct it, because if we change it a bit to the right, some more stuff will fail. If we put it to the left, other stuff will fail. So we could try and run other algorithms to maybe find more correctable errors in this and try to advance it. It's all kinds of highly mathematical algorithms which we run on these kind of results. So this is in short how our application looks like. That was it. Thank you all.
Johan, I think you're going to be very popular outside when you go out the stage, because you have a lot of questions. It's actually pretty hard to pick which is the best one, so I'll go with the ones that were voted. So, did you hit any physics limits that make the chip improvements harder? What is the long-term vision of making chips faster?
Yeah, so that question, it comes back a lot of times, like, hey, you reach atom level, what are you going to do? Yeah, of course, I mean, there are limits, but so far, we still manage to beat them. Like the stuff we now do with EUV light, in the past, no one thought it was possible. Even our competition, they didn't try it because they thought it wasn't possible. And once we managed to do it, they said we won't try it because it's too expensive. So to give an idea, nowadays we spend 4 billion a year on research only. So if another company wants to do this, you need and the people and a lot of money. And we still manage to go smaller and smaller. If there is a limit, yeah, time will tell, I guess.
Yeah, there was a question about atom size, so I guess you answered that as well. The other question is, how did the growing demand of GPUs impact ASML growth? As it has happened to NVIDIA, there must be a correlation? Question mark?
Yeah, so there is like a cycle of sales in these machines typically. So what you typically see is that we sell a lot of these machines for like 7 years, and then it's a bit lower, and then it takes up again. So we're now in a period where sales actually went down. So it's quite weird. We hear all these AI stories and increased demand for chips, but actually the number of requests we get from companies went down. We still have a backlog for like a year to build new machines for our customers. But in the past, we would get more orders than we get now. So actually, it's a little bit going down. And one of the theories that I heard was that actually the whole AI market, if you look at the revenue of all these companies, that revenue is still relatively small if you compare it to the total revenue of companies that buy chips. So while it's an interesting market, I think we expect growth in it. At this point in time, it's not that huge yet.